Here's a question for you. What's the probability of a randomly chosen person from the United States being a student at Iowa State University? Well, obviously it's a pretty small probability, right? You could compute it exactly. It would be the total number of students at Iowa State divided by the total number of people in the United States, so the total population. And of course that's a really small number, it's a really small probability. But what if I were to change it up? What if I were to say, what's the probability of a randomly chosen person from the United States being a student at Iowa State University, given that they also live in Ames? Well, obviously that changes things up quite a bit, right? Because I'm now only looking at people in Ames, and the vast majority of students that attend Iowa State do live in Ames, right? So this is really going to change my probability once I say given that the person also lives in Ames. And this is an example of what we'll be studying over the next couple of sections. It's an example of conditional probability. So this is the notation we'll be using. It's the probability of A given B, and it's what this is the probability of the occurrence of event A given the occurrence of some other event B. All right, so I'm asking what's the probability of a person being a student at Iowa State given that they also live in Ames, and this is what we call conditional probability. Right? It's what's the probability of A given the condition of B already occurring. And I guess we'll just jump straight into, I'll tell you how to compute this. This will be the next question. How do I find the value of something like this? And I'll just give you the formula. Obviously, I need A and B to occur, right? It's the probability of A given event B. So I'm looking at probability of A and B. But I don't want to look at the probability of A and B relative to all possible outcomes. I know that B occurs, so I actually end up scaling this. I rescale this by just dividing by the probability of B itself. Okay, so I'm not giving you a true derivation of this formula, but obviously I want the probability of A and B occurring, and not relative to everything, relative to just the event B. So you end up dividing by the probability of B. And this is how you compute conditional probability. It's just use this formula. Of course, I don't want to divide by 0, so I'll just make this note that the probability of B can't be 0 in this formula. So yeah, there's our formula, and I guess we'll jump straight into examples of using this in computing conditional probability. So we'll come back to our favorite experiment, just rolling a fair 6-sided die. And the first question I have here is actually not conditional at all, it's just what's the probability of rolling a number greater than 3. So this is what we've been doing over the last couple of sections. Let's call this event E, the event of rolling a number greater than 3. So of course we've got 4, 5, or 6. And this means that the probability of this event, of rolling a number greater than 3, is just the number of elements in E, so 3 of them, over the number of elements in the full sample space. And the sample space is, of course, when you roll a 6-sided die, is 1, 2, 3, 4, 5, 6. So 3 over 6 is our probability, or 1/2. But now let's get into a conditional question. What's the probability of rolling a number greater than 3, given that an even number is also rolled? Wouldn't be too hard to think about this intuitively, but I want to formally use our formula. So we've got event E again. E is 4, 5, and 6. But let's call event F the event that we know already happens, an even number is rolled. So F is 2, 4, or 6. So this is asking, what's the probability of event E given event F? Right, this is what I want to know. What's the probability of rolling a number greater than 3 given that F actually happens? Given that an even number is rolled. So we'll use our formula. This is the probability of E and F over the probability of F. So there's a problem here, is I haven't looked at the event E and F, so let's do this really quickly. E intersect F is what? What's the intersection of these two events? We've got 4 common to both of them, and 6. So this is 4 and 6. Okay, so the probability of E intersect F is there's two elements in here, so 2 over 6. Right, it's a number of elements in E intersect F divided by the number of elements in those sample space. So 2/6 over the probability of F occurring. There's 3 elements in here, so the probability of F is 3 over 6. So what's this equal? Well, how do you divide fractions? You flip them. You flip the bottom and multiply, right? So you multiply by the reciprocal. So this is 2 over 6 times 6 over 3. The 6's cancel, and my answer here is just 2/3. Again, intuitively, what is this saying? Intuitively, I know that F has occurred. Right? So the question now is, what's the probability of rolling a number greater than 3 given that F has occurred? Well, either this happens or this happens, right? Either I roll a 4 or I roll a 6 to get a number greater than 3. So how many ways can I roll a number greater than 3 given that F happens? Well, 2 out of 3 possibilities, hence 2/3. So computing conditional probabilities isn't that bad, right? It's just using this formula. It's the probability of event E given event F is you take the probability of their intersection divided by the probability of the event that you already know happened. We'll do another example. So now we'll come back to our other favorite experiment is drawing cards from a standard 52 card deck. All right, so the question is, what's the probability? So we draw a card. The question is, what's the probability that the card is, and we'll do a couple examples here. So A, the probability that the card is a heart, given that it is red. Again, intuitively, this isn't hard to think about. I know that exactly half of the red cards are hearts, the other half are diamonds, so I would expect this probability to be 1/2, right? Just intuitively, there's not a whole lot of calculation to do here, but what I want to do is practice using the formula. So very formally, let's say A is the event of drawing a heart, and B is the event of a red card. Okay, so what's the probability of drawing a heart? Well, there's 13 cards of each suit over 52 cards, so this is 13 over 52, or perhaps more intuitively, this simplifies to there's exactly 1/4 of the deck is a heart, right? So this simplifies down to 1/4. And the probability of drawing a red card, the probability of B, well, half of the deck is red cards, so that's 26 cards over 52. Or again, more intuitively, because half of the deck is red, that simplifies to 1/2. So, what about A intersect B? This would be the event of drawing a red heart, right? Event of a red heart. But notice that that's a bit redundant, right? All hearts are red. So the event of drawing a red heart is really exactly the same as event A. It's just the same as drawing a heart, right? So the probability of A intersect B is still just the probability of A, which is 1/4. Alright, so here you have to realize that A intersect B is a bit redundant. The event of drawing a red heart is still just the event of drawing a heart. Okay, so what do we want to do? We want to compute the probability of A given B, conditional probability here. And our formula tells us we want to take the probability of A and B, or A intersect B, over the probability of event B. So probability of A intersect B, we already have that, it's 1/4, over the probability of event B, which is 1/2. How do we divide fractions? We flip the bottom and multiply, right? So this is 1/4 times 2 over 1, which is 2/4, or as we already said, intuitively, the answer should be 1/2. Right, so if I've drawn a red card, exactly half of them are hearts, so I would expect the probability of A given B to be exactly 1/2, which we found using our formula. So let's do a slightly different example. So we're still drawing a card from a standard 52 card deck, and the question now, B, is what's the probability of drawing a heart given that it's a face card? So we'll set up our events again. A is an event of a heart. And we already have that the probability of drawing a heart is 13 over 52, or 1/4. And B is the event of a face card. So remember, face cards, these are jacks, queens, and kings. There's 4 jacks, 4 queens, 4 kings, so 12 total face cards in the deck. So this is 12 over 52, which I think simplifies. This simplifies, it's divided top and bottom by 2 at least. This is 6 over 26, or 3 over 13. Okay, so the event of drawing a face card is 3 over 13. And what else are we going to need? We're going to need A intersect B. Right, so the event of a heart face card. So probability of A intersect B is what? Well, remember there's 12 face cards, right? And for each face, jacks, queens, and kings, there's exactly 1 heart of each, right? You've got 1 jack of hearts, 1 queen of hearts, 1 king of hearts. So there's 3 total heart face cards over the 52 cards in the deck. So the probability of A intersect B is 3 over 52. And 52 is not a multiple of 3, so that can't be simplified. And what are we looking for? We want to know the probability of A given B. And the conditional probability of A given event B, we'll use our formula. This is the probability of event A and B over the probability of B. So this is 3 over 52 over the probability of event B, 3 over 13. So that's 3 over 52 times 13 over 3. The 3's cancel. 13 over 52, that is just 1/4. So that's interesting. The probability of drawing a heart, given that it's a face card, is 1/4, but that's the exact same as just the probability of drawing a heart in the first place. All right, so notice, that's just the probability of A. And if you think about it, that's kind of expected, right? Exactly 1/4 of the deck is a heart, and exactly 1/4 of all face cards is a heart. So being told that you've also drawn a face card shouldn't really affect the probability of drawing a heart at all, right? Which means we have a term for this. If the probability of A given B is exactly the same as just the probability of A, so being told that event B didn't change anything, or being told that event B occurred didn't change anything, then we say they're independent events. Event A is independent of event B. Being told that I drew a face card didn't change the probability of drawing a heart at all, because they're independent events. So let's come up with a definition for this. So here's a formal definition. It actually doesn't look much like what I just spoke about, but we'll come back to that in just a second. But we say that events A and B are independent if the following happens. If when you take the probability of A intersect B, that's just the probability of A times the probability of B. Alright, so there's the formal definition for independence of events. If someone asks you, are 2 events independent? Well, all you would have to do is check this formula. Check, find the probability of A intersect B, and ask yourself, does that equal the probability of A times the probability of B? If yes, then they're independent. If not, then they're not independent, they're dependent. But this doesn't look like what I mentioned with the probability of A given B being the same as the probability of A. So let's derive that. So notice that if A and B are independent, then what happens? The probability of A given B it's the probability of A intersect B over the probability of B. And if they're independent, then probability of A and B is just probability of A times probability of B. So this is P of A times P of B over P of B. Those guys cancel, and it's just the probability of A. So this matches up with our intuition from the last example, right? This is what we're getting at when we talk about independence, is that B occurring didn't change the probability at all. Right, so the probability of A given B is still just the probability of A for independent events. So, and also, you could go the other way around too. Probability of B given A is probability of A intersect B over the probability of A. I guess maybe it doesn't matter if I write A intersect B, but maybe to respect the order of things here, I'll write probability of B intersect A. And once again, because they're independent, probability of B intersect A is probability of B times probability of A over probability of A. Those cancel, and I just have probability of B. Alright, so once again, they're independent, so being told that A occurred doesn't change the probability of B occurring at all. This is what independence is getting at, right? Being told that one event happens doesn't affect the other, it doesn't affect the probability of the other event occurring. But this is formally the definition. If you want to check if two events are independent, just check if this equality holds. Coming back again to one of our favorite experiments, now we're tossing a coin twice. We've looked at this a fair coin twice. We've looked at this quite a few times. So our sample space is, of course, I toss two heads, or a heads then a tails, or a tails then a heads, or tails and tails. And I want to look at it if two events are independent or not. So let's define two events. A will be the event of tossing a head on the first toss. So event of a head on the first toss, and this would be the subset consisting of HH and HT. And event B will be the event of a tails head or tail. Should that be pluralized? Event of a tail or tails? I don't know. Event of a tail on second toss. So what would this correspond to? Tail on the second toss would be HT or TT. And the question is, are events A and B independent? Are A and B independent events? In other words, this is asking intuitively, is the event of tossing, or does the event of tossing a head on the first toss, does that affect the probability of tossing a tail on the second toss? Well, coins don't have any memory, right? The second toss should be completely independent of the first. It shouldn't matter what I toss on the first toss, or what shows up on the first toss, that shouldn't affect the second toss at all. So intuitively, yes, I very strongly expect that these are independent events. But let's actually, let's demonstrate this. So A intersect B, this would be the event of a head on the first toss and a tails on the second toss, which would just be HT. It's the event common to both of them. And the probability of A intersect B is 1/4, right? One element over 4 elements. So this is just 1/4. Well, another way to write 1/4 is as 1/2. Let's not do it this way. That's 1/4. And let's also compute probability of A times probability of B. What's the probability of A? Probability of A is 2 elements over 4 elements, so 2 over 4, or 1/2. And probability of B is again 2 over 4, or 1/2. Multiply them together, I have 4/8. Oops, not 4/8. 4 times 4 is 16. 4/16, which is 1/4. So indeed, these two numbers are equal, right? The probability of A and B is 1/4, which is exactly the probability of A times the probability of B. So the conclusion is that yes, because I have equality of these two numbers, then they are indeed independent events. So A and B are independent. Another way you could have computed this is you could have said, what's the probability of A given B? Right, well, that would be the probability of A and B over the probability of B. Right? What's the probability of event of a head on the first toss given that I tossed a tails on the second toss? And once again, if you compute this expression, this is 1/4 over 1/2, which is just 1/2. And that's exactly the probability of A in the first place. Okay, but let's just come back to this. If you want to show two events are independent, just compute that probability of A and B is equal to P of A times P of B. So we have one more thing to talk about. I want to talk about the product rule and building probability trees. It'll lead nicely into the next section. So the product rule is a useful way for computing the probability of intersections, and it's just rearranging our formula for conditional probability. So the probability of A given B is probability of A and B over probability of B, but if I rearrange this, this means that the probability of A intersect B, or A and B, is just probability of B times the probability of A given B. And this is what people usually call the product rule. But also, if I were to look at the probability of B given A, well, that's just the probability of A intersect B over probability of A. So if I rearrange this, this means probability of A intersect B, intersect B, is I have a slightly different formula here, but it's the probability of A times the probability of B given A. Alright, and these are usually referred to as the product rule. And they can be really, really useful for computing the probability of intersections. It's useful for computing the probability of the intersection of two events. And I'll show you what I mean by using an example. Alright, so here's a fairly complicated example. It's two balls are drawn in succession without replacement. So I'm drawing a ball from a box and I'm not going to put it back in when I'm done. So two balls are drawn in succession without replacement from a box that contains 4 red balls and 2 white balls. What is the probability of drawing a red ball on the second draw? Well, what I'm going to do is I'm going to build, when things get this complicated, I build a probability tree. So build a probability tree. It really gives me all outcomes and the probability of each outcome. So build a probability tree. And what I mean by this is, okay, so I've got my start event. And what's the first thing I do is I reach into this box and I draw a ball, right? So one of two things can happen. I either draw a red ball on my first draw, or I draw a white ball. What's the probability of each of these happening? What's the probability of drawing a red ball? Well, there's 4 red balls, 2 white balls, so 6 total. So the probability of drawing a red is 4 out of 6. Right? Meanwhile, the probability of drawing a white ball is, there's 2 white balls out of 6 total, so 2/6. And I could simplify this. I could write this as 2/3 and 1/3, but I'll leave it like that for now. So here's the first draw. And then what do? Well, then I do it again, right? Then I've got my second draw. And on the second draw, I either draw a red ball, so I'll call it R2, or a white ball. And similarly down here, I either draw a red ball or a white ball. Here's where we really have to think about the probabilities, right? So what's the probability of drawing a red ball the second time around if I drew a red ball the first time around? Well, alright, so there were 4 red balls, right? But I drew one. I drew a red ball and I took it out. So how many red balls are left? 3, right? How many balls are left total? Well, there's 3 red balls now and still 2 white balls. So the probability of drawing a red, if I drew a red the first time, is now 3 red balls out of 5 total. All right, so you might need to think about that a little bit, but just ask yourself, okay, if I drew a red ball out, how many balls are left? 5. How many are red? 3. Similarly, what's the probability of drawing a white ball the second time? If I already drew a red one out, well, how many white balls are left? There's 2 out of 5 balls total. So this is 2/5. Now we would play the same game down here. I'll label each of these branches with the probability. If I drew a white ball out, what's the probability of drawing a red ball the second time? Well, there's still 4 red balls in there and only 1 white ball left, right? So this would be 4 out of 5. And the probability of drawing a white ball the second time, there's only 1 white ball left in the box out of 5 balls total, so this is 1/5. Right, so what are these probabilities getting at? Right, for example, this probability right here that I've listed, 3/5. What is that? That's the probability of drawing a red ball the second time, given that I drew a red ball the first time. Alright, that's what these are getting at. And what I want to know, what's the question? The question is, what's the probability of drawing a red ball on the second draw? Well, that would be the probability of drawing a red ball on the second draw, and let's write it like this. The probability of drawing a red ball, right? It's just the probability of drawing R2. What would that be? Well, there's 2 ways to get here, right? There's 2 ways to get to R2. I either progress down this branch or I progress down this branch. All right, so the probability of drawing a red ball is actually going to be the sum of these 2 probabilities. It's either the probability of drawing a red ball on the first draw and a red ball on the second draw, plus the probability of drawing a white ball on the first draw and the probability of a red ball on the second draw. Can you see that? These are two mutually exclusive events, so if I want the probability of drawing a red ball, I just have to add them together. I have to add the probability of drawing a red ball this way or drawing a red ball this way, because there's two ways to do it, so I just add them together. And now how do I compute the probability of these two intersections? So R1 intersect R2, here's where the product rule comes in. Right? Product rule says this will be the probability of R1 times the probability of R2 given R1. And the probability of W1 intersect R2 would be the probability of W1 times the probability of R2 given W1. So what are these? What's the probability of R1? Well, we already have them all these numbers that we need are written down here. It's 4/6. 4/6 times the probability of R2 given R1. Well, we already noted that's what this number is, right? That's 3/5. Plus the probability of W1 is 2/6. Times the probability of R2 given W1, that's what this number represents. All right, so times 4/5. And now all I have to do is simplify this. I'm going to do this all in one go. My denominator in both cases is 30. Right? 6 times 5 is 30. Here I have 12 over 30 plus 8 over 30. This is equals 20 over 30, or 2/3 is the answer. All right, so the probability of drawing a red ball on the second draw is the sum of all the different probabilities for drawing a red ball on the second draw. And to get them, we use the product rule. But I want to point out that I don't normally think about formally using the product rule here. I would never do this, right? When you're going through these problems, and it's asking you what's the probability of R2 occurring, well, just think, okay, how many ways can I get to R2, right? How many branches, how many paths take me to R2? I want to add all of the probabilities of those branches together. And how do I get the probability of each branch? Well, I just multiply the numbers along the path. Right, so the probability of getting R2 in this case, a red ball on the second draw along this path was 4/6 times 3/5. And the probability of drawing a red ball along this path was 2/6 times 4/5. Right, so you don't really have to formally think about the product rule when you're doing these problems. When you have a probability tree, just multiply the probabilities together. And I like probability trees a lot, and we'll do more examples of these, but I'll put them off to the next section, so 8.4.